Hello everyone and welcome to your 10.3 video notes. This video will also continue on to lesson 10.4 video notes. Starting out with lesson 10.3, more uses of substitution. This could actually probably be titled Advanced Uses of Substitution. In lesson 10.2 we did practice substitution, primarily where both equations were solved out, y equals. Both equations in the system were given in the form y equals. Today we are going to have to solve one of the system's equations for a variable to substitute in the other in order to make that happen. A warm-up for you, solve the equation for the given variable. Go ahead and press pause and take the time to do each of these examples. Hopefully you've come up with something that looks like this. Y equals 2x minus 5 for the first equation. Solving for c in the second equation, hopefully you've come up with something like this. C equals 0.5d plus 2.5. And in solving for n in this last equation, hopefully you've come up, for m apparently, hopefully you've come up with something that looks like this. If we solved for n as it originally directed, hopefully you would have come up with something that looked like n equals negative 0.5m plus 2.5. So again, if you followed the directions as given, in this last one here, hopefully you have come up with something that looks like this. N equals negative 0.5 m plus 2.5. Continuing on, as we take a look, solutions to the systems by substitution. The solution to a system was the ordered pair x, y that satisfies both equations. These directions are identical to those that you saw in lesson 10.2, so you actually don't even have to write them down again. I'm just highlighting the first step because this is typically the part that we didn't have to do in the first one. We didn't have to rewrite one of the equations, so for today you may occasionally have to rewrite one of the equations so it is solved for x or y. Then of course substitute the expression, and then solve the equation to find the value of one of the variables, use the unknown to find the other value. You're going to see a few examples run through here, including that highlighted step that we didn't really use in the last lesson. Last time, both equations were in the format of y, or b equals in this case, so the substitution was pretty easy. Today you're going to see something like this where one or neither of the equations says y equals, where we'd have to solve the equation and then do a little bit of a more complex substitution. So again, instead of calling this more uses of substitution, we could easily call this advanced uses of substitution. So we're going to check out an example here, actually the one that you saw on the last page. X minus y equals 5. And 8x plus 2y equals 10 are the two equations of our system. They're the two conditions that must be met. The first equation can easily be solved for x or y. Solving for x, we would get x equals y plus 5. And solving for y, we would get y equals x minus 5. Either one of these could be substituted into the second equation. I'm going to use the first one because it doesn't use subtraction, which means there aren't going to be as many negative numbers to me. So I'm going to substitute for x in the second equation. So you can see me substituting y plus 5 in for x in the second equation. Now we have a variable that, an equation with just one variable. There's no y squared, so no quadratic is necessary. We'll start with the distributive property. Distributing the 8 gives us the equation 8y plus 40 plus 2y equals 10. Combining our like terms, we see 10y plus 40 equals 10. Eliminating the constant by adding the opposite, of course, 10y equals negative 30. Eliminate the coefficient now by dividing. It turns out that y equals negative 3. Now that we know that y equals negative 3, we can substitute y to find x. According to what we found earlier, x is equal to y plus 5. So using our value of negative 3, I find out that x equals 2. If I check this in the first equation, x minus y equals 5, yes. If I check it in the second equation, 8x plus 2y equals 10, turns into 16 plus negative 6, yes. So this is a valid solution that x equals 2, y equals negative 3. Writing your own system, just to be clear on the steps here, determine the two conditions, define some variables, and then translate your conditions to equations. So if we were to take a look at this example where the owners of a carnival have found that twice as many children as adults come to the carnival. If 3,570 people attended the carnival, write and solve a system of equations that represents the situation. The first condition, twice as many children as adults. The second one, 3,570 people attend the carnival. I'm seeing two variables here, the number of children attended and the number of adults attended. I will define them as C and A. Equation from condition number 1 is that children equals twice the adults. And the condition number 2 gives us the equation C plus A equals 3,750. This is our system of equations to be solved. As for in-class examples, this is what we're going to be tackling, covering in class. You should try them on your own to measure your understanding. In lesson 10.4 portion of the video, we're going to talk about solving systems by addition. This is often referred to as another name, solving systems by elimination, in various other textbooks, as well as in the Brightstorm resource and the Khan Academy video resource that you can find linked to our Moodle page. Today we are going to talk about how to solve systems of equations by adding. Just as a reminder of our warm-up, the addition property of equality, which we talked about in Chapter 2, says if A equals B, then A plus C equals B plus C. Essentially, if two things are equal, they're still equal if the same thing is added to both sides. It's used to solve things like x plus 4 equals 7. If I add negative 4 to both sides, they're still equal, but the results can give us x equals 3. This is true even if the two things that are added, that are the same, don't look identical. This is kind of an extension on this, is if A and B are equal, and then C and D are equal, I can add A plus C, and it will be equal to B plus D, since both of the parts in A and C were equal to the parts of B and D. So keep in mind x plus 4 equals 7, and also that 1 plus 3 equals 2 times 2. I can add the 1 plus 3 to both sides, or excuse me, the opposite of 1 plus 3 on one side and the opposite of 2 times 2 on the other side, and I still come up with a result of x equals 3. So we're going to extend this idea to look at systems of equations today, adding the same things to both sides. So in a system of equations, we are given two equations. We can use the two equations to create a third equation by addition. For example, this system of equations shows two different ways of writing two different quantities. The two green expressions represent the same thing. 4x minus 3y is the same as negative 50. The two orange expressions represent the same thing as well. 7x plus 3y is the same as negative 5. I know this because it says they are equal. If I add either of the green expressions with either of the orange expressions, so I'm adding a green plus an orange, I will also have two equal quantities. So on this side, a green plus an orange comes out to be 11x. Remember, when we add things together, only like terms combine. So when I add, only the x terms combine to give me 11x, and then only the y terms will combine, and they're opposites, so they actually come out to be 0. Over here, we're adding just two numbers. They add up to be negative 55. In this case, those opposite y's did zero out, and we can easily solve for x by dividing both sides by 11. We find out that x equals negative 5. If we wanted to take this a step further and not just find out what x equals, but actually find the solution to the system, we can easily substitute, just using the second equation here. I chose the second equation because it didn't have the subtraction. And substituting our x as negative 5, we find out that 7 times negative 5 plus 3y equals negative 5, which really means that negative 35 plus 3y equals negative 5. Undoing that addition piece, we come up with 3y equals 30 by adding positive 35 to both sides, and we find out that y equals 10. Now, since I used the second equation, I'm pretty sure the answer fits here. I'm going to check in equation 1 as well. And by entering x equals negative 5, y equals 10 in the first equation, it comes out to be a valid check as well, that negative 50 is equals out to negative 50. This is solving systems by addition. There are two basic steps. These are the steps you should write in your notes. Number 1, add the two equations together with opposite terms for one of the variables to eliminate the variable. You may have to multiply one of the equations by -1. 2, solve for the remaining variable. So as we take a look here, in this particular equation, or excuse me, system of equations, we have r and s variables. I'm noticing that the first equation compared with the second, the r terms are opposite. If I add a green with an orange and a green with an orange, the result that I will see is -3s equals -6. Our opposite r terms zeroed out. -5s plus 2s is -3s. And over here, -7 plus 1 is -6. -3s equals -6 is very easily solved for s by dividing by -3, and we find out that s equals 2. Using one of the two equations, and you can use either one, I use the first one here. 3r minus 5s, we just calculated out that s was equal to 2 is equal to -7. As we solve this equation, we find out that 3r minus 10 equals -7, or that 3r equals r by adding 10 to both sides. That got rid of this and made this side a 3. We find out that r equals 1. We've got a check 1, or excuse me, a check 2, where we are trying out the substitution of r equals 1, s equals 2, and it does come out to be a valid check 2. The next equation, or excuse me, the next example, we're just going to go ahead and take a look at pretty much the same steps. We're going to add the two equations together. The result is 3/2 m equals -15. Using a multiplication of a reciprocal here, we find out that m is actually equal to -10. Using that along with the second equation, we can find out that n equals 25. Since I use the second equation to find the value of n, I'm going to do a check 1, and check 1 comes out to be true as well. Now you may have noticed that we haven't used the asterisk yet. That will happen actually in our next example, where in this one I have 2c plus d equals -80 and -3c plus d equals 120. You'll notice we have the same d term, but not an opposite d term. Sometimes the terms are not opposite, but they are identical. So before solving by using addition, you should multiply one of the equations by -1. It doesn't matter which one. I chose the second one because instead of having -3c then, it made a positive 3c. You'll notice that multiplying by -1 changes each term to its opposite. -3c becomes 3c. Plus d becomes -d. Positive 120 becomes -120. Now I'm ready to proceed like normal. Adding the two equations together, the d's will zero out, leaving us with 5c equals -200. Using division, we can find out that c equals -40. Substitution into the first equation will tell us that 2 times -40 plus d equals -80. So -80 plus d equals -80. We just found out that d equals 0. Since we used equation number 1 to find d, I'm going to do a check 2, and it works out an equation. I'm sorry, this is actually a positive calculation. For a second there, it didn't look like it worked out. -120 equals positive 120, but a negative times a negative is a positive, which would result in a positive 120. So check 2 works out perfectly, and we know we have found a valid solution. These are the 3 examples that we'll be taking a look at in class. You should be looking them over now to prepare yourself with questions and things that you want to talk about during class.